So we're going to continue into chapter 3. This lecture might be a little less intense from the first one. We're looking at addition and subtraction of whole numbers. Now remember, we're looking at this from a conceptual perspective as teachers. So we're not just looking at what is 2 plus 3. We want to think about how can we teach this in a way so that when they get to algebra and they see x plus 2 and they know that 3 plus 2 is 5, they can find x. So we're moving towards higher order thinking concepts, and we're being very intentional with how we teach these basic concepts so that when they reach those points, they can be successful. So we're looking at number relationships that are going to be found from comparing and ordering numbers, which in algebra is going to really help them with inequalities. We're looking at the meaning of addition and subtraction by looking at a couple of different models, but recognizing that all students learn differently. So we don't want to teach just one method to our class. We want to find something that suits most of the learners by showing different strategies and then allowing them to really connect with what's meant for their line of thinking. We're going to look at some of the properties. You're definitely going to want to take notes in this lecture. And we're going to look at the inverse relationship between addition and subtraction. So if I'm looking at the addition of whole numbers, counting on is an addition strategy where addition is performed by counting on from one of the numbers. So for example, 5 plus 3 can be done by showing 5 fingers. So you're counting on 5 and you're adding 3 fingers to get to 8. Now, while that may seem intuitive for us, at the lower level, students might not understand that you start at 5 and you go count up 3 fingers. They may think that 5 is the first finger you're counting from this. So while this seems intuitive to us, we have to really put ourselves in the mindsets of our learners, and we have to say count on 5 up 3 digits. So really be intentional about the word choice there so we make sure we are teaching them the proper way to count and where to start from. Now, a set model is going to be a little bit different. So this is going to be your hands-on kinesthetic learners. It says, suppose Jane has 4 blocks in one pile and 3 in another. If she combines those two groups, how many objects are there in the group? So in this case, we would have them count 1, 2, 3, 4, 5, 6, 7, 8. And we would just have them counting both of those individual groups into one large group. Now, what does that actually mean? That's going to actually be teaching them set notation from last week. That's set A and set B. So I'm adding those together so that when we teach them sets, we can go back and say, hey, remember when we did addition and we had 4 in this group and 3 in this group and we added them together? That's where the sets are coming from. So we're preparing them for higher order thinking, even while they're at a lower level. Notes that sets can't have any elements in common, which meaning A and B can't share a block. The block has to be either an A or in B. And this is another great strategy you could even do with them in your notebook. You could have them draw 4 dots and have them draw 3 dots and count them all up. You don't have to actually have the physical blocks to work with students in that way. So the addition of whole numbers then can be tweaked. If your student really likes the set method, we can actually say, well, then for whole numbers, if you want to add A and B, you're going to add the number of things in group A to the number of things in group B. Are you going to write this notation on your chalkboard? No, you're not. But you're going to be intentional about using the word group A, group B, and adding them together to get the total, because then when somebody comes behind you, they've already got that idea of having one group and another group, and you're combining those groups. So it's being intentional with what we're doing so that later on our students are more successful. Now, if I have a number line, this is another way to help a student. If Josh has 4 feet of ribbon and red ribbon and 3 feet of white ribbon, how many feet did they have all together? So you could draw 4 red ribbons and then go from that 4, 3 more down for the white ribbon and count them up together would be 7. So you're just using hash marks. It's similar to the set idea, but you don't have 2 separate groups because you're just continuously drawing. Another example would be the one with Gail. So these are some basic ways to show this on a number line for students. I start at 0. I have 4 feet of red ribbon and 3 feet of white ribbon. And really, it's helpful if you use colors that you can do on your board. So if I said 4 feet of blue ribbon and 3 feet of red ribbon, then I could actually show it in those colors. And I say, okay, all together I have 1, 2, 3, 4, 5, 6, 7. So it's having them use those hash marks to quantify what's happening in the problem. So students have to understand that the sum is going to be those two arrows combined. So it's going to go to the endpoint of the second arrow, and that we can't overlap things with using this method, which students may try to go from 3 over, but when we're adding, we're not going to have any overlap there. So the sum then is read as the endpoint of that linear thinking. So this is really for your students who are linear thinkers who maybe don't do as creatively or well hands-on, but they're still visual. So we want to define now that we've figured out how to add numbers. Let's start looking at ordering numbers and comparing them. If I have less than, then I'm talking about things that are less than a value. So something that is written as, say, 2 is less than 3. And only if there exists some number, and this is where the definition helps here, a plus k equals b. So what is this saying? If a is less than b, so say 2 is less than 3, in order to get to 3, I'm going to have to add something. So all this is redefining what is less than, and I want to redefine less than in a way that makes sense at the lower level. And I say one number is less than another if you would have to add something to that lower number to get the higher number. And the great example would be 2 is less than 3 because I'm going to have to add 1 to 2 to get to 3. And if you notice, we're teaching some principles of algebraic thinking there. So we're helping students think about abstract numbers and what the abstract numbers being put into an equation creates. So then I want to talk about, there's a closure property of addition. Are you going to teach your first graders the closure property of addition? No, you're not. But you're going to teach them the principles, and then when it comes up in their algebra class, they're going to have a scaffolded idea of how to work with this. So if A and B are whole numbers, if I add them together, I get whole numbers. So all this means is I can't ever get a decimal out of something where I'm adding two whole numbers. So that's what a closed property means. It means that whatever group you're doing the operation with, the result is going to be the same group. So with whole numbers, if I'm doing 2 plus 3, then I'm going to get a whole number answer. And that's something that's going to be unique to whole numbers. And I'm going to get a unique whole number from that. So 5 plus 2, 5 is a whole number, 2 is a whole number. It's always going to give me a whole number. This is great when you first start introducing decimals to your students and you're trying to work through when are you going to get a decimal answer versus when you're going to get a whole number answer, especially when you start intermixing those problem sets where they're applying both of those concepts. So it's somewhat healthy for the student to think, oh, I have this mixed review. These are two whole numbers. My answer is going to be a whole number, not a decimal. So then they don't second guess themselves and try and work off of that. Now, we have a commutative property of whole numbers, which tells us it doesn't matter the order that we add in. We're going to get the same thing. So 3 plus 5 is 5 plus 3. This is something to really emphasize as you're doing your addition facts because it reduces the addition facts students have to learn by half. So if they know what 3 plus 8 is, then they know what 8 plus 3 is. So if you're helping them to see that pattern right from the onset of addition, it's going to make all that fact learning so much easier because the synapses is formed in their brain so that they can just think, oh, what is 3 plus 8? I know 3 plus 8, so I can do 8 plus 3. The associative property starts happening when we're adding 3 or more things together. So I want you to add 2 things in this group and get a group by itself, and then add this other group of C. Again, it's addition. It doesn't matter the order I do it in, I'm going to get the same thing. So what the associative property tells us is I'm grouping 2 things together, and then I'm adding to that last thing. And it doesn't matter what order I do it in because it's addition. The identity property is really, really important to start using even at the lower level with our students because we want them to realize that 2 plus 0 is 2 and 0 plus 2 is 2. So when we teach those addition facts, saying, hey, this is an identity property, and the reason it's an identity property is because you get the same thing. So 2 plus 0 is 2, so I have 2, I get 2. That's what makes it an identity property, and that's really vital when they move on in their math careers. So if we can start incorporating that word at the lower level, it's going to be extremely helpful. So let's look at a few examples. 5 plus 7 equals 7 plus 5. So right here, we're emphasizing the fact that it doesn't matter the order that I do the addition in, I'm going to get the same thing, which means it could either be commutative or associative. Associative only happens when I have 3 or more numbers and I'm setting a group aside with parentheses. So this has to be a commutative because I only have 2 numbers and I'm not trying to create a subgroup. Then in part B, I'm taking a whole number, I'm adding a whole number, and I get a unique whole number. I'm adding 2 number system classifications together. That's going to be our closed property of addition. So this is going to be similar to what you're going to see in the lab. The lab can't test you on how to teach things, but we are trying to test you to see if you're understanding what we're asking you to consider as you're teaching. In part C, now I have 3 or more things, and I'm grouping them together, which is going to be the commutative property because, wait for this, I grouped them together with parentheses, but did I move the parentheses themselves? I did not move the parentheses themselves. So what that means is that it's commutative and not associative. But if you look at the bottom, I moved what was going on here. So this could be seen as commutative or associative because I changed the order that I'm adding that +2 in. It went from being added last to being added first. So those are 2 tricky places. To really be associative, we're looking for something different to be in the parentheses on the left from the right. That's really what we're looking for when we're saying associative. So if I want to talk about counting on, I'm going to start with the larger number. So 4 plus 2, I would start on 4 and add 2 fingers. What we want to avoid is teaching students to do 2 plus 8 and starting with 2. It's much easier to take 2 plus 8 and say, hey, this is commutative, so we can write it as 8 plus 2. So start with 8 fingers and then add 2 fingers. So it's the commutative property is very helpful for counting on and teaching students it's okay to start with the second number. For doubles, after students master doubles such as 3.3, we can also work on skills like doubles plus 1 from the associative property. So if I have 6 plus 6, that's a double. We know 6 plus 6 is 12. And if I want to add 1, that's going to be 13. So 6 plus 7 can be rewritten as 6 plus 6. And then you got the 1 hanging out. And that's how we get 13. Now for us, this is not going to be intuitive probably for this generation because we didn't learn it this way. My son has come through Common Core and he adds faster than I do. Hundreds times faster than I do because he uses this exact strategy. So while you may not see the payoff of this strategy immediately in your elementary classroom, it is vital to what's happening in the upper levels when they're working with very large numbers. So the whole idea of the remainder from changing our base systems is being applied here because if I have 6 plus 7, that's 6 plus 6 with a remainder hanging out. And so that's feeding into this method of teaching us stronger mental math. Now, one of the ways we can build upon this is regrouping to form groups of 10. So if I have 8 plus 5, I can take that and break it into 5 is 2 plus 3. Why do I want to do that? Because if I do 8 and 2, that gives me 10, and it makes it easy to see that it's 13. Again, this is not intuitive for most of the teaching generations, but it is so helpful as students move up. So they're borrowing to complete an entire cycle of 10. That is the idea of what's going on there. Counting back is usually used when one number is 1 or 2 less than 10. So for example, because 9 is 1 less than 10, then 9 plus 7 is 1 less than 10 plus 7. Now, a lot of us learn to do like hand tricks and things like that. We're trying to avoid that. So again, we're trying to borrow 1 from 7, and that makes it 10. So 10 plus 6 with that borrowedness is going to be 16. So we're trying to count back to groups of 10. So let's frame these around subtraction. There's a couple different subtraction models. There's the takeaway. So you're going to start with the large number and you're going to take away the number of objects by crossing them out, by lowering your fingers, or some type of method there. Then there's the missing added model. If you have a student who is a phenomenal adder, then maybe you want to teach them how to do subtraction in terms of adding. My son totally gets the adding model. My daughter cannot do the adding model to save her life. So she has to do the takeaway model. These are not going to meet the needs of every single learner if they were just presented by themselves. We're wanting to present both so that we have the most successful students possible in the class. Next would be the comparison model, would be how many more one quantity is than another. And then again, we can use the number line model. That's actually a really good one for a lot of students who are visual learners. So if I'm in the takeaway model, 8 minus 3 would be I have a group of 8. I'm going to cross out 3 blocks. How many do I have left? If I'm looking at the missing addend, I'm going to say, okay, 8 minus 3. This can be thought of as the number of blocks that has to be added to 3 to get to 8. So I would rewrite 8 minus 3 as 3 plus something is 8. And since 3 plus 5 is 8, I know 8 minus 3 is 5. This is going to be your very high level thinkers. This is not going to be a method for the average student or the below level student that needs extra help. This is going to be something that your high level learners are going to go, oh, yeah, that makes sense. Or your really strong addition people, it's going to make sense. And we want to show it to them because it's going to teach them algebraic thinking, which is going to allow them to progress much quicker. However, we don't want to show a struggling student, we don't want to push this model on them. We can show it, but we don't need to push it as the only thing they can do. Here's an example of the number line. If I'm at 8 on the number line and I take away 3, where does that put me? Or if I'm at 3, how far do I have to go to get to 8? And they're going to count from 3, 1, 2, 3, 4, 5. So you can use that model. It's slightly related to the addition because you're kind of counting up, right? You're starting at 3 and you're counting up to 8. So that forms a synapses between addition and subtraction for those students. So if I'm looking at subtraction is really addition of a slightly different fact here. So we can teach that. If we have a comparison model, we're lining them up exactly, and we're counting who doesn't line up, who is the remainder. So you see this idea of the remainder, it keeps coming back around to you. The number line, we could also do 5 minus 3 would be to start at 5 to move backwards 3, which would put us at 2. So this is just another number line model strategy that you can show students. Properties of subtraction doesn't have as many properties as addition. So we do know that subtraction is closed. One whole number minus another whole number is going to be a whole number. So we can start using sentences that have symbols to prepare them for algebra. So this is introducing an algebraic concept to those students. So I can say 9 plus 5 is sunshine. What is a sunshine? And they're going to tell us 14. 12 minus a diamond is 4. Can you figure out 12 minus what is 4? So a lot of times we're just, instead of saying X, we're saying what, or we're inserting that actual symbol in there. And so if we know that the sun is 10, is 9 plus 5 equals 10 true or false? Then we can actually extend that learning experience for our higher level learners, and we can start giving them statements with those symbols and say, hey, is this true or false? And if a value makes it true, then we tell them, yeah, that's a solution. And that is such a vital concept in Algebra 1. We ask them so many times, is this a solution? And they need to understand it's a solution if it's true. So when you're extending this, as your students become ready for this extension, we want to level them up so that they're building the scaffolding for that algebraic thinking.